category for Final Jeopardy is the Sun-Earth connection. And the answer is the ghostly light that produces the dance of colors in the night sky in the northern hemisphere. The correct question, of course, what is the Aurora Borealis, or Northern Lights? Hello, everyone. I'm Alex Trebek, the host of the popular quiz show Jeopardy! You know, as a child growing up in Northern Ontario, Canada, I was always fascinated about the mystery of the Northern Lights. In this episode of NASA Connect, host Jennifer Pulley and special co-host Dr. Sten Odenwald will take you all on an adventure to explore the Aurora Borealis. You'll learn about the many legends and myths that revolve around the aurora throughout the history of mankind. You'll also learn how NASA scientists and engineers use satellite technology to measure and analyze aurora data. You'll visit Norwegian scientists at the Andøya rocket range located just inside the Arctic Circle in Norway. And in your classroom, you'll use data analysis and measurement to plot the auroral oval and to determine the heights of the Northern Lights. All in this episode of NASA Connect, Dancing in the Night Sky.
Welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. I'm Jennifer Pulley.
And I'm Sten Odenwald, an astronomer at the NASA Goddard Space Flight Center.
On this episode of NASA Connect, we are filming on location in Norway, a Scandinavian country located in northern Europe. Today, Sten and I are at the Viking Ship Museum in Oslo, Norway.
And right beside us is an ancient Viking burial ship called the Oseberg. And you know, it dates back to the 9th century.
Wow.
So, Sten, let's fill them in. Why are we in Norway?
Because Norway is one of the best countries in the world to see the Northern Lights.
Or the Aurora Borealis. Aurora was a Roman goddess of the dawn, and Boreal is a Latin word meaning north, thus the Northern Lights. There's a lot of folklore about the Northern Lights, and various cultures from around the world have explained them as dancing spirits or blood raining from the clouds. The Vikings believed the Northern Lights were beams reflected from the shields of the Valkyries, female warriors serving their god Odin. The Aboriginals of Scandinavia, or the Sami, believed that the Northern Lights had supernatural powers to resolve conflicts. The Sami painted auroral symbols on their magic drums. In Middle Age Europe, the Northern Lights were thought to be reflections of heavenly warriors. As a reward, the soldiers that gave their lives for their king or country were allowed to battle on the skies forever. There are so many myths and legends and superstitions that have revolved around the Northern Lights throughout the history of mankind.
By the mid-1800s, scientists finally began to explain many of their mysteries. Like lightning or earthquakes, they are natural events, not supernatural ones. By the turn of the 20th century, scientists actually created artificial aurora in their laboratories. Christian Birkeland, a famous Norwegian scientist, created this device called the Torella, a magnetic sphere representing the Earth. Currently housed at the Norwegian Technical Museum, this device creates artificial aurora by using an electron gun similar to the one in your TV picture tube. Birkeland believed that currents of electrons from the sun caused the aurora. He laid the groundwork for the modern-day study of the Northern Lights. Today, thanks to modern research satellites, we now have a deeper and more complete understanding of how the Northern Lights work.
Say, do you remember what the Final Jeopardy category was at the beginning of the program? Well, if you don't, it was the Sun-Earth connection. And Sten, isn't it true that the sun is the source of the auroras?
That's right, Jennifer. The sun does play a role in producing the aurora. The aurora are the only visible evidence that we have that the sun and the earth are a system that are connected by more than just gravity and sunlight. You see, the sun gives off charged particles called ions. These ions travel out into space at speeds of 350 to 700 kilometers per second. A cloud or gas of such ions and electrons is called a plasma. The stream of plasma coming from the sun is known as the solar wind. The sun's corona, or outermost atmosphere, continuously emits the solar wind, a stream of electrically charged particles, mostly protons and electrons, flowing out in all directions. It is commonly said that the aurora's gorgeous curtains of light are caused by particles flowing directly from the sun. But this is not the case at all. When a major solar storm interacts with the Earth's magnetic field, it causes some parts of this field to rearrange itself, like rubber bands pulled to their breaking point. The magnetic energy that is released causes powerful currents of particles to flow from distant parts of the magnetic field into the atmosphere. These currents flow along the magnetic field into the polar regions and collide with nitrogen and oxygen atoms in the atmosphere. The color of the aurora depends on which gas, oxygen or nitrogen, is being excited by the electrons. Oxygen emits either a greenish-yellow light, the most familiar color of the aurora, or a red light. Nitrogen generally gives off a blue light. The blending of these colors can also produce purples, pinks, and whites.
Stan, that is fascinating. And of course, it's beautiful.
That's right, it is beautiful. And you know, the northern lights are always moving, like giant curtains of light, weaving and swaying across the sky.
So Stan, how do scientists study the northern lights?
Well, besides photographing them from the ground, there are 3 other ways that scientists like to study them: ground-based measuring devices, sounding rockets, and satellites. Data can be collected from these 3 methods and analyzed by scientists to get a complete picture of the Aurora Borealis. To get a better idea of how ground-based instruments and sounding rockets are used, let's visit Professor Alv Egeland at the Andoya Rocket Range.
But before we visit Professor Egeland and learn more about the rocket range, let's review the 2 math concepts for today's program: data analysis and measurement. Data analysis and measurement are 2 important math concepts to scientists and engineers. You see, before things can be analyzed, they must first be measured. Scientists and engineers take measurements so they can collect data. Think about what you measure every day: length, volume, mass, or temperature, to name a few. Once scientists and engineers collect the data they need, then they must analyze that data. Scientists are constantly on the lookout for patterns that can help them understand how things work. By analyzing data, they can construct relationships among numbers and the scientific principles they are investigating. Now that you understand the importance of data analysis and measurement, let's go meet with Professor Alv Egeland.
How is a magnetometer used to measure auroral activity?
In analyzing the graph, what indicates a great disturbance in the Earth's magnetic field?
How are sounding rockets useful to scientists and engineers?
Professor Egeland, how are you?
Fine, thank you. And how are you, Jennifer?
I'm wonderful, I'm wonderful. This is Dr. Odenwald.
Hello, Professor.
Hello, Dr. Odenwald. Nice to meet you.
Good to meet you, too.
You know, the Andoya Rocket Range is an exciting facility. Can you tell us some more about it?
Andoya Rocket Range is the furthest north permanent located rocket range where we launch rocket and scientific balloons. It's located here because it's just under the Auroral belt. And this is the place where we do all the launching of rocket and balloons from Norway. The range provides complete services for launch, operation, data acquisition, recovery, and ground instrumented support. Since 1962, more than 800 rockets have been launched from this range. We have also hosted scientists and engineers from more than 70 institutes and universities around the world.
Professor, what kind of ground-based measurements do you take here at the range?
Well, we take a lot of different measurements, but I think the most important is the recording of the Earth's magnetic field, and for that type of recording we use a magnetometer.
A magnetometer. Sounds like an instrument that measures magnets or maybe a magnetic field?
You are on the right track, Jennifer. A magnetometer can be used to measure weak, short-term variation in the strength of the Earth's geomagnetic field. It was first used in the year 1800 by Alexander von Humboldt to study aurora and what he called magnetic storms. These variations are due to electric currents in the upper atmosphere. The electrons and ions flowing in from distant regions of the Earth's magnetic field cause currents to flow in the ionosphere. and also cause the aurora currents. So a magnetometer measures a quantity that is directly related to the northern lights. The stronger the magnetic variation, the higher the auroral activity.
Professor, this is just one type of magnetometer, correct?
That's correct, yes.
Now, how do you analyze the data that you collect from a magnetometer?
What we do is really we reproduce some graphic representation. And if there is a big deviation from the local standard field, we call it a magnetic storm. And I just want to show you one example here of a big magnetic storm. And here you can really see big deviation from the local standard field. The following graph shows a relatively weak magnetic storm. The magnetometer measures the geomagnetic field along three axes: north, south or H component, east, west or D component, and up, down or Z component. This graph is a magnetic field strength versus time plot. Now here is a plot of a relatively strong magnetic storm, probably caused by a disturbance in the solar wind. What can we conclude from the two graphs?
Let me see. The second graph shows more magnetic activity than the first graph. So I would say the more magnetic activity, the greater the auroral activity.
That's correct, Jennifer. Notice in this section of the graph, the deviations are at the maximum. If the night sky was clear, we can view the mysterious and beautiful aurora colors. Magnetometers located here at the range are continuously taking measurements of the local geomagnetic field. In fact, anyone from around the world can visit the following website to analyze the geomagnetic activity around the Andrea rocket range.
Professor, you mentioned that this facility is known for auroral research using sounding rockets.
Yes, that's correct. As a matter of fact, that's the main purpose for the rocket range. We can study the aurora from the ground, but then we just look on the bottom aurora. If you study the aurora from a satellite, you just study the top of the aurora. But by using instrumented rocket, you can study the inside of the aurora. That's why sounding rocket is such a unique platform for auroral studies. Other instruments on the rocket register electric field and magnetic field and count particles coming into the atmosphere from distant part of the Earth's magnetic field. Consequently, the energy that produces the northern light can be calculated. During an ordinary winter night in Norway, the northern light involves more energy than the country uses in 1 year. A severe auroral storm can produce billions of joules of energy per second.
Professor Eglund, thank you. We learned so much.
It's really my pleasure. Thank you too. Or as we say in Norway, gleden var på min side.
Okay guys, now it's time for a cue card review. How is a magnetometer used to measure auroral activity? In analyzing the graph, what indicates a great disturbance in the Earth's magnetic field? How are sounding rockets useful to scientists and engineers? So, did you get all the answers to the questions? Good. Now, let's review. We've learned about the myths and legends surrounding the Northern Lights, and we also learned how ground-based instruments and sounding rockets are used to study the auroras. Now, we turn our focus to space. Later in the program, Dr. Nikki Fox will tell us how data analysis and measurement are used to study the auroras with the help of 2 NASA satellites, Polar and Timed. But first, Sten will give us the scoop on image.
Thanks, Jennifer. Aurora tell us in a dramatic way that something invisible is happening above our heads in space to light up our skies. We can use sophisticated Earth-orbiting satellites to learn more about the causes of the aurora. The Imager for Magnetosphere to Aurora Global Exploration, or IMAGE, is a NASA satellite that lets us see the invisible activity that swirls around the Earth and eventually causes aurora to appear. When a solar storm collides with Earth, one of the first signs of the disturbance is a collection of particles called the ring current. It's an invisible river of charged particles extending over 30,000 kilometers from Earth. Much of the matter in this current actually comes from the Earth's upper atmosphere in gigantic plumes and fountains of gas from the polar regions, but we still don't know how the particles get their energy. Another part of the upper atmosphere, seen by image for the first time, is what scientists call the plasmasphere. It extends out into space at least 10,000 kilometers. You should think of it as the outer limits to the ionosphere. During severe storms, parts of the plasmasphere are stripped off, but then reform as new gas flows out of the Earth's upper reaches. And of course, image also provides scientists with movie-like high-resolution views of the aurora seen from space. Over the South Pole, the satellite dips down to 1,000 kilometers to show us never-before-seen details in auroral structure. The aurora in the South Pole is called Aurora Australis. Over the North Pole, we see a more distant view and a bigger picture. We can relate this big picture with views of the ring current and plasmasphere to track the evolution of an aurora from cradle to grave. The reason why we're so keen to understand the aurora is that the aurora are kind of like a final examination. If we can really understand how they work, that means we also understand all the other things about Earth's environment as well. We have billions of dollars of satellite technology in space, astronauts living and working in space, and on the ground, many kinds of systems that are affected by solar storms. An electrical blackout in Canada back in 1989 cost billions of dollars. We have lost over $2 billion of expensive communication and research satellites in the last 10 years alone. Solar storms have tremendous potential to cause damage to us. Only by understanding aurora and the events that lead up to them can we improve our ability to predict how to avoid the harmful effects of space weather storms. The real challenge is to get enough early warning that a storm is approaching. That's why it's also important to look at the sun for clues to the next storm.
Thanks, Sten. Okay, guys, now it's your turn to apply data analysis and measurement skills with this really cool activity. Sten, they are gorgeous, aren't they?
Aren't they amazing?
Hi, we're students from the Region School right here in Andenes, Norway.
NASA connected us to show you this activity. It's called Where to See an Aurora.
You can download the lesson guide and a list of materials from the NASA Connect website.
Here are the main objectives.
Students will find and plot locations on maps using geographic coordinates, draw conclusions based on graphical information, convert centimeters to kilometers using a given scale. Here are some terms you will need to know. Latitude, a geographic coordinate measured from the equator, with positive values going north and negative values going south. Longitude, a geographic coordinate measured from the prime meridian, which is the longitude that runs from Greenwich, England, with positive values going east and negative values going west.
Good morning, class. The northern lights are seen most dramatically in only certain places in the northern hemisphere. Today, you will plot the location and boundaries of a typical auroral oval in the Arctic region. You will see its geographic extent and determine its relationship to familiar continents and countries.
Distribute all student materials. Students can work alone or in pairs. Students, label the latitude lines beginning at the center point with 90 degrees. Then mark each circle 10 degrees less than the previous circle, ending at 20 degrees. Next, label the unmarked longitude lines. Plot the points onto the geographic grid for the outer ring. The geographic data points can be found on the student activity sheet. The points are identified as ordered pairs, longitude-latitude. For example, the ordered pair 180-60 means 180 degrees longitude and 60 degrees latitude. Connect the points in the outer ring. Now, plot the points onto the geographic grid for the inner ring and connect the points. Using the scale 1 centimeter equals 1,400 kilometers, measure, in kilometers, the approximate width of the shortest and longest distances between the inner and outer rings and determine the range. Record these values on the student activity sheet.
Okay, class. From the analysis of your graph, how far is the center of the auroral oval from the North Pole?
I calculated that the center of the auroral oval is about 500 kilometers from the North Pole.
Very good, Marita. And where would you travel in North America to see the Northern Lights?
From the graph, either Canada or Alaska are the best places to view the Northern Lights.
Students, once you complete the hands-on activity, check out the web activity for today's program called the NASA Northern Lights Challenge. It can be accessed at the NASA Connect website. This activity is created to be fun, interactive, and will challenge your ability to solve problems. During the course of the activity, you'll use various probes to explore properties of the planets in our solar system. There are 8 interactive probes in different colored boxes along the 2 sides. You'll learn about the temperature, magnetic field strength, solar wind density, atmospheric gases, mean distance, mean density, gravity, and speed on other planets. Upon exploring each planet, you will apply what you learned to solve the following problem. What other planets may have the northern lights? Special thanks to the students from Brandon Middle School and Lansdowne Middle School in Virginia Beach, Virginia for demonstrating this web activity.
Super job, you guys. So, what is NASA doing to study the auroras? Well, Nikki Fox, a senior scientist at the Johns Hopkins University Applied Physics Laboratory in Baltimore, Maryland, can tell us all about it.
Why do scientists use satellite images to monitor the auroras?
In analyzing the graph, when do auroral activities increase?
What are the phases of the aurora?
This is the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland. I am the operations scientist for the Polar Mission. The Polar Mission is part of NASA's Sun-Earth Connections fleet. Within the Sun-Earth Connections fleet, Polar has the responsibility for multi-wavelength imaging of the aurora, measuring the entry of the material into the polar regions, the flow of material to and from the ionosphere, and the discharge of the energy in the ionosphere and the upper atmosphere. Scientists use satellite images to monitor the position of the various auroral features. In particular, the latitudinal location of the edge closest to the equator of the aurora determines the amount of activity. The further the aurora moves towards the equator, the bigger the event. Also, the extent and speed of the expansion of the aurora tells us a lot about the amount of activity. The further and faster it moves, the larger the event. Polar is a unique spacecraft because it carries 4 different cameras to study the aurora. There is a high-resolution visible imager, which allows us to look at the aurora in different wavelengths or colors. In this way, we can simultaneously image the red, blue, and green components of the aurora. There is also a global imager, which allows us to look at the whole Earth at once. This camera takes pictures in ultraviolet, so we can see what the aurora is doing, even when there is sunlight in the way. Auroras do occur during the daytime, we just can't see them with the naked eye. But from the images of this camera, we can see the size of the auroral oval. For example, the following graph shows you the latitudinal auroral extent for selected coronal mass ejection events. Coronal mass ejections, or CMEs, are gigantic explosions caused by the sun that can reach speeds of millions of kilometers per hour. It takes around 3 days for a CME to reach the Earth. The vertical axis of the graph is the geomagnetic north latitude from 40 degrees to 58 degrees. On a globe, 40 degrees north latitude is closer to the equator and 58 degrees north latitude is closer to the geomagnetic North Pole. The horizontal axis represents the dates of selected CME events. From analysis of this graph, we can determine that the latitudinal auroral extent generally increased from 1997 to 2000. Be careful in the way you interpret this graph. The function appears to be decreasing. Even though the data show a downward trend, the auroral oval extended closer to the equator. For this particular graph, it tells us that the auroral activity increased. Let's look at 2 data points. From the data on January 10, 1997, there was an auroral event in the northern hemisphere that extended to a latitude of 57.3 degrees. Do you know the name of the country that the auroral oval covered? If you said Canada, then you are correct. On July 15, 2000, there was an auroral event that extended to latitude 41.2 degrees. The auroral activity was so intense that the auroral oval stretched into the southern parts of the United States. The 11-year solar cycle of the Sun reached its maximum in the year 2000, so we expected auroral activity to increase from 1997 to 2000. With all these cameras and the data we collect, we can photograph the evolution of an aurora. The evolution of every aurora tends to follow a similar sequence. We call this an auroral substorm. The following images show a typical sequence of an auroral substorm. The first image shows a quiet oval before any activity begins. This is called the quiet phase. Right before we see any bright emissions, we can observe the oval getting bigger and moves further towards the equator. This is called the growth phase. The activity truly begins with the small spot of light, or onset event, followed by the lighting up of the whole ring and an expansion to a more poleward location. The large bright region you can see is called the auroral bulge. When the aurora reaches its maximum expansion, you can see that the large bulge begins to break up and the small discrete features appear. Finally, the whole aurora dims and recovers. It will eventually return to the initial state, the quiet phase. The whole process may repeat over and over again until the activity dies out completely.
Now, all the images you've seen so far have been from the northern hemisphere of the northern lights, or the Aurora Borealis. But did you know that there was also a southern counterpart of the aurora called the southern lights, or the Aurora Australis? And here we're seeing a unique movie taken by the Polar spacecraft that shows us both the north and the south at the same time. This allows us to see that the activity is occurring at the same time in both hemispheres. We call this the conjugate aurora. Now, we've seen data from many different cameras on the Polar spacecraft and learned that when you add them all together, you can learn an awful lot more about the aurora. Now we're looking at an animation which shows the polar auroral image underneath with the timed spacecraft flying over the top. Timed is taking images in very high resolution, and you can see that every time the spacecraft flies through the oval, it suddenly illuminates all the fine-scale features that you couldn't see before. So now we know that when you add two data sets together, you get even more information. Now, with the addition of data from ground-based observatories and sounding rockets, we can look at the aurora with full perspective.
Okay, now it's time for a cue card review. Why do scientists use satellite images to monitor the auroras? In analyzing the graph, when do auroral activities increase? What are the phases of the aurora?
Well, that wraps up another episode of NASA Connect.
We'd like to thank everybody that helped make the show possible.
Got a question, a comment, or perhaps a suggestion? Then write us at NASA Center for Distance Learning, NASA Langley Research Center, Mail Stop 400, Hampton, Virginia 23681. You know, each year here in Andenes, they celebrate the beauty of the auroras with the Northern Lights Festival.
We leave you now with some images of the festival and the people of Norway.
So until next time, stay connected to math, science, technology, and of course, NASA. We'll see you then. Goodbye from Norway.
Bye-bye.
Captioning funded by the NAC Foundation of America.